Yeah. So just to clarify things, how many of this among the students, how many of you are engaged in numerical simulations? Oh, that's a lot. And discrete simulations? Oh, many fewer. Okay. Okay, good. So when we speak, and the notion of potential energy landscape is familiar to everybody? Yeah? No, not everybody. Okay, so I'll start by a bit of motivation. The idea of this type of effort is to try to identify some mechanism of deformation that might be general, or at least for some broad class of materials. Here we have heard a lot about soft material. And usually if we think of colloidal suspensions or foams, we have length scales that are larger than hundreds of nanometers or maybe hundreds of nanometers. And we have stresses which are in the range of pascals, kilopascals, and energies which are essentially in the range of the thermal energy at room temperature. Actually, I was a bit surprised. I realized that we never heard about temperature until now. When we start to, very little, when we start to look at harder systems, in fact, we have systems which like polymers or metallic oxides, oxide glasses, we have much smaller length scales, much larger energies, and associated with these much larger stresses. And temperature starts to be, well, usually when you do a soft condensed matter, you are working at room temperature, you play with density in order to change the property you have of your systems, you have a lot of parameters to change the interactions. When you play with glasses, you have atomic glasses, you have much more leeway, much less leeway. You have materials with fixed interactions, and if you want to flow the materials, you usually have to heat, so your temperature starts to play a role. So I like to start with motivating this by some work on metallic glasses. So metallic glasses might seem to be a bit unusual materials. So they are essentially metals, metallic alloys, usually with a complex composition of atoms that can be produced in amorphous form. And okay, so there are lots of, there have been a lot of interest for that because of their magnetic or mechanical properties. For the matter here, what's interesting, it's really just an example where, because of the interest for that material, we have, for some system, a very complete experimental map of the type of behavior. And I think that's what's interesting, is that you can see here, as a function of strain rate and temperature, people have, so first of all, you see these systems can be extremely ductile. They can also yield. Of course, you have some fragile rupture. They can show non-Newtonian rheology, and here you see a lot of flow stress versus strain rate curves where you show this shear thinning behavior. And so the point is that the people have obtained this map, and on this map you see that you have two parameters. You have the strain rate, you have the temperature. Of course, when you are at high temperature, at some point you reach the liquid regime. And so at high temperature, you are in the liquid. You see that there are some things which are not very trivial in the relation between strain rate and temperature. And then when you are at lower temperature, you're properly speaking of the glass. So whether we think of, what I like about this map is that on the same map, you see the plasticity of solid, you see the Newtonian behavior, and you see the non-Newtonian regime. Okay? So if you, for example, take a cut through this map here, and you were plotting the stress versus, oh, that should be strain rate here, strain rate, you should see a Newtonian regime and something here which is a shear thinning, and you would say that I have a shear thinning fluid with Newtonian and shear thinning. If you were taking a cut here, sorry, this is the strain rate. Here you would say that you have something with, in fact, you could not really do tests with as a function of strain rate, or you at different strain rate, you would see brittleness, and you would see the system reaching failure. So, all of what I'm going to talk about is really follows from an effort to understand, first of all, the low temperature material, solid, and then to understand how what we can understand about the low temperature plasticity can extend to higher temperatures. The outline of the talk is first, I'm mostly gonna speak about athermal quasi-static simulations, and which is, I'll explain that a bit just shortly, that it's a way to access the low temperature, low strain rate limit, as the name indicates. I will look at case studies, and then the goal will be, and that's probably will be for the later talk, to go at finite strain, to introduce progressively finite strain rate and thermal effects. So, but before we go to understanding finite strain rate thermal effect, we will need to understand what happens in the solid. So today I'll focus essentially on the plasticity, on the plastic response of the solid. So as the title of the talk says, I want to introduce a potential energy landscape perspective on plasticity. So I'll talk about plasticity, on plasticity and flow. What do I mean by that? The potential energy landscape, so for those who are not familiar with the concept, simply we have a system with particle positions. So you have n particles, which have positions Ri, they have also velocities. And if we think of an atomistic system, and I think that's also, I should have said, one interest of looking at glasses is that in opposition with, in soft condensed matter, you have all sorts of complexities arising from the presence of fluids, from the complexity of the colloidal interactions or the structure of foams. In glasses, you have something much simpler. You have atomic systems, and you know that all the forces derive from a potential. And so you have a function which is the potential energy is a scalar function which depends only on the positions. And this is the potential energy surface in the sense that you have now, here you have, if you are in dimension d, you have n particles. So you have a system which is n to the d dimensional. So this is a horribly complicated object because our mind doesn't work in dimensions higher than 3. It's just very hard for us to understand anything beyond dimension 3. Even dimension 3 is difficult, right? And anything beyond that is impossible. So we are looking at a surface because it's a scalar function in an n-d dimensional space. and why is this thing matter is that because when you are in a solid, by definition, a solid is a material where the force is, which is mechanically balanced. Atoms are jiggling, they might be jiggling around due to thermal fluctuations, but they jiggle around what? They jiggle around in equilibrium positions, a mechanical equilibrium position. Mechanical equilibrium means that the forces on any particle is 0. And the force on any particle is the derivative of the potential on the position of particle I. And so a mechanical equilibrium point is just a local minimum of the potential energy surface. Okay? And so solids lie, so if you have a crystal, you have a single local minimum, which is the crystalline structure. And the thing about glasses, the thing about disordered material, is that you have a huge amount of local minima. And so the potential energy landscape consists of an enormous amount of local minima. Can I erase this? On the eraser was not maybe, oh, okay. Okay, I'll just draw here. So the potential energy landscape consists of, I'll try to draw this in 2D. So you have local minima, and around each minimum, you have some basin of attraction. So you have points which are, if you just put the system in one point and let the energy relax, it will go down to this local minimum. And between these basins of attractions, you have saddle points that you can use, the system can use to go between a minimum and another minimum. Okay, so the point is that a solid and a disordered solid is a system which exists in local minima of the potential energy surface. And so so now the problem we have, and I'll just show you shortly why that matters. So the problem we have when we do simulation, it was raised in one of the talks before, is a problem of timescales. We know that numerical simulations, we have to, if we want to study dynamics, we have to solve Newton's equations, and we have to sample, we have to cut the time axis and iterate over the time axis over small times compared to the vibration time. The vibration time in atomic systems is extremely small, 10 to the minus 13 seconds. So you have to cut fractions of a picosecond. So you have to cut, to integrate your dynamics over very small time intervals. And maybe you can accumulate in a reasonably large system 1 billion time steps. That's already a big effort. And if you do that, you access times which are a fraction of a second at most. So if you want to simulate shear, well, if you want to, over the maximum accessible time, you want to shear your system by 100%, which even for steady flow maybe is not enough to reach steady flow, right? Most experimentalists would shear for hundreds of percent before reaching steady state. You have to shear at a rate which is 10 to the 4th second, which may not be where you want to see the important phenomena. And so, yeah, there is a problem, there is an issue, a priori, there is an issue with timescales. So the idea of the ephemeral quasi-static limit is to bypass, is to find a way to avoid the problem of timescales. The idea is that, as I said, if we are in a glass, in a solid, at really low temperature means that at low temperature, so you are very low below the glass transition temperature. If you are very low below the glass transition temperature, your solid essentially is quenched, is trapped in a single local minimum of the potential energy landscape. And the thermal fluctuations are completely irrelevant. So you no longer need to simulate the thermal fluctuation. The only thing you need to know is where your local minimum is. Right? So then the idea is, okay, let's take first the limit of very low temperature. And it's relevant because when you are below 80% of TG or 50% of TG, the alpha relaxation time is up in the sky. And so the relaxation, the thermal relaxation, I'll come back to that, a priori doesn't matter at all. So if it doesn't matter at all, you can just first take the T to 0 limit. And taking the T to 0 limit means just bringing the system to mechanical equilibrium. And then what happens? Well, nothing. You can wait and wait and wait. Right? If you extrapolate alpha relaxation time for glass, it's beyond the age of the universe. So you can really wait for a very long time. The only way to have something interesting occurring is to shear. And when you start shearing the system, now you force the system to change. And so the athermal quasi-static limit is the idea that you take first T to 0. And when you are, so when I say T to 0, again, I'm saying that I will only look at local minima of the potential energy landscape. I bring the system to a local minimum. And then I will apply shearing at a very slow rate. And how does that do that in practice? So you take your favorite system, you minimize the energy, and then you apply a very small increment of strain. And we will come to how small is small. So you apply a small increment of strain and repeat. Extremely simple. You minimize, strain a bit, and re-minimize. So what happens when you do this is that, as I explained, these basins, when you have a local minimum, in general, a local minimum is surrounded, and this is topology, this is catastrophe theory. Every local minimum is surrounded by a basin which has a finite volume, except when the minimum becomes unstable, so which are really singular points. So around the minimum, you have a domain of the potential energy landscapes. You have a basin of attraction where the system, every system will converge. So if you take a system in a minimum and you bring it a bit out of the minimum and let it relax and re-minimize, it will come back to the same point every time, okay? So now what happens when you strain? If you apply a very small amount of strain, what happens is that you will distort the potential energy surface. You won't do anything catastrophic. Small means that you very continuously change the basin of attraction, the minimum and its basin of attraction. When you do this, the minimum position of the minimum changes. So you strain a bit your system and let it relax, and it will follow adiabatically the local minimum that you consider, where the system starts from. You can repeat, and you can
the energy landscape. Yeah. So via the boundary condition, or
okay, I will think mostly of periodic systems, but it doesn't matter. I could have walls. I have an energy function. And the whole this is completely general. It doesn't depend on periodic on the type of boundary condition you choose.
Energy is not explicitly dependent on the strain. So you said
you're right. You're absolutely right. I should have said that the potential energy depends also on the shape of the box, which is, in fact, H here is a matrix. In fact, you're absolutely right. So if I want to shear a system, I need to introduce Bravais vectors, and H is a matrix of the Bravais vectors. It's the tensor product of the Bravais vector. Okay. So the potential, when I introduce strain, you're absolutely right. I introduce an extra parameter in the potential energy surface. And when I strain my system, I change the potential energy surface, and I change continuously the basin, the structure of the potential energy surface. Okay? So I can go in a direction, and if I have, for example, not periodic boundary conditions, but walls, this parameter is just here encodes the positions of the wall. You could imagine that you have confining your system by walls. The potential energy that you consider is the potential energy of your atoms and of this system with the confining walls. And the parameter here is the relative position of the walls. So this is, you can do this in a general case. So when you deform continuously your minimum, you can go back. And if you go back, you're sure to revert to exactly the same location. So the point is that so long as you distort a local minimum continuously, the system, the response is adiabatic. It's completely reversible. So there is a single thing that can happen to introduce irreversibility. It is that occasionally, the basin of attraction of your minimum, of course, when you do this in general, if you load your system, you will increase the energy of the system. You will increase the stress. And so the system will be in a state which is increasingly stressed. And what it corresponds to in potential energy landscape is that the basin of attraction of where your system lies will shrink. And at some point, you have to reach a catastrophe, meaning that the minimum suddenly vanishes. Right? So you shrink your basin of attraction to zero, and now this point, the minimum becomes unstable, it becomes a saddle point, becomes unstable, and now the system has to go somewhere. So if you look at a stress-strain curve, what I show here, so it's a small system. It's 20 particles on the side, so about 20 by 400 particles, I don't know, something like that. So every circle you see is a position of a local minimum of the potential. It's a state produced by the dynamics. So it's discrete because I have to use small increments. Yes?
It's counterintuitive that if you clear the system, then you reach even deeper minimum. I thought you will increase your energy.
So that's exactly right. So when you load, here you have the elastic. So you let me maybe describe it. I think I'll answer to your question. So you have here the sequence of the states that are produced by these dynamics. Each circle is corresponds to a local minimum that you identify of your potential energy landscape. You start from a minimum. Actually, maybe you start from here, and the system was not at zero stress. Because, well, when you take a glass, arbitrary glass, it's not, the stress is not in small sample, it's something. So you load your system, and here what you see is that as you load, you ramp up stress. And this is the elastic response. And that's what you expect, that when you load, you increase stress. But occasionally, and then you see these jumps, and these jumps correspond to all these plastic events. So from time to time, the local minimum becomes unstable. Now it has to go down. Because you are in the basin, and the basin shrinks, and now it becomes unstable. Your system, we minimize the energy, so the system has to go down here. So it has to go down. And sometimes it's a very tiny jump, and sometimes it's a very big jump, and I'll come back to this a bit later. So we will speak about elastic segments or elastic branches to refer to these parts of the stress response which corresponds to the adiabatic tracking of local minima. And then we have something called plastic events, which are these jumps. Okay? So there are consistency requirements to do that in a proper way. The consistency requirement is that you use, first of all, you need to minimize the energy accurately. There is a hidden parameter, which is how well you minimize the energy. And there is another parameter, which are the steps you take. And let me say for now that the steps you take just must be small enough that you resolve this continuous response of the local minima. Of course, if you take very big jump, you might miss, if you take very big strain steps, you might miss all the interesting information, and then what you do is a nonsense, right? So you need, the problem is you need to have small enough strain steps so as to resolve the continuous elastic response, and then you have these local plastic events that you resolve. I would like to make a comment. Suppose that you have an elastic, perfectly plastic material. Macroscopic, a very large sample. So you have a stress response where I should have started with a quiz on that. So you have stress versus strain, you load, that's a macroscopic sample, and then you reach plasticity. What dissipates energy in plastic flow? Can somebody tell me what dissipates energy in plastic flow? What determines the rate of energy dissipation?
Viscosity or internal friction?
So this tells you something different. It tells you that, dissipation comes only from the jumps. So the viscosity is a final mechanism of dissipation. You have plastic events that release energy, and this energy hits, or this energy triggers some vibration of the system, which has eventually to be dissipated, and eventually it is dissipated by viscosity. But the rate of energy release is just the size of the jumps. And this is uniquely fixed by the potential energy landscape and by nothing else. So, not by friction, not by, just fixed by the structure of the potential energy landscape. Actually, I like to that's just a sort of historical pause. This guy is not the Brillouin you know, yeah?
Two previous slides, because I don't get what happens to the potential energy.
Yeah.
Because here in the picture...
You are right, I should have drawn the potential energy.
No, in the left picture. In the left picture.
Here?
Okay, with the plastic step,
yeah,
I get it that the potential energy become more smooth.
So you are in a basin,
Okay.
and the basin shrinks. So maybe let me draw it like that. I will draw it in another way. So you have your potential energy. Let me write U as a function of a certain degrees of freedom. So at some point, you are in some kind of potential energy landscape like that, and the system is here. And when you strain, this thing becomes locally unstable, and the system jumps here. That's it. But sometimes it might be more complicated. It might jump low. Okay? The point is that when you have an instability, you know you have an event. You don't know where you will end. And I will come to that. We will discuss plastic events at length after. Yes?
You would plot the energy of a system together with a stress curve?
You have branches of parabola. Yeah. And jumps. The same jumps. yeah, so historical pause. So this is not the Brillouin you know. This is the father, Marcel Brillouin, who wrote in 1904 a notice of a sort of summary of his past work, 200 articles on everything from resistance and electricity and lots of things. And he worked on friction. And he wanted to understand what is the mechanism why you dissipate during friction. And of course, he knew that you had conservation of energy and biomechanics. And then he has this that so that's the French for the people who can read French. This is the English translation. This is just, so he has an argument where you look at the problem of two magnets and you approach a magnet, you move, basically he's looking at a system with a bistable system. And he showed that if you have a bistable system, you can drive slowly and you have a reversible response. And if you drive more, at some point you have a jump, and then you are losing reversibility. And so he was saying, in fact, the paper on friction was in 1899, and he was saying that, so I read an isolated mechanical system subjected to slow external deformation, which can be considered reversible as long as we do not examine the stability of the state of equilibrium. So it means we are looking at, from the microscopic viewpoint from far away, becomes a seat of irreversible internal modification as soon as a cycle includes unstable states. This is just completely amazing that they were deducing this just. And essentially, irreversibility is introduced in rational mechanics with instability. That's exactly the point I want to make, is that dissipation and dissipation in a perfect plastic flow is strictly the consequence of mechanical instability. And it's completely controlled by mechanical instability. Okay? Of course, we need to understand this instability a bit better. So before we go down, so we have these branches and events. And so we will look a bit in detail at first the elastic response and then at the plastic response. So it was noted a long time ago that, and I will show you a bit more why, that if you look at the two things, that if you look at the elastic response of a glass, so they were not looking at plasticity properly. They were taking a sample of a relaxed glass and looking at the strain response and measuring elastic moduli. And if you're a theoretician, one thing you can do, in order to measure a modulus, is you can assume that if you strain your system, you could assume, well, you talked about non-affinity. I'll give a bit more detail on that. So yeah, Luca talked about that. But so you could assume that the response of the system is affine. Affine means that you're shearing your system. And so affine means that all the particles are following the affine, are just the prescribed average affine deformation. You apply a strain, and so you suppose that you have a displacement field, which is just exactly, let me draw like that, which is exactly that prescribed by the average strain. So that's the affine motion. And we could imagine that if we shear a system, we know the potential of interaction between atoms. So we want to calculate the elastic response. And a way to do this is to say, let's assume that all the pairs of particles are changed according to the macroscopic strain and calculate the resulting elasticity. And what happens is that if you do this, you find Lemaitre constants that it turns out that's in 2D. In 3D, it's a bit different, but you have Lemaitre, no, it's the same. So you have Lemaitre constants that are equal, which is a problem because for you cannot have a big variety of Poisson ratios. And now if you understand that when you shear a system, this is just what I was describing here, when you shear a system, the position of the minimum is a bit different. So you look at the linear response of the system, but in the linear response, when you shear, the linear response to shear, the position of the minimum shifts a very tiny bit. Now, this shift is taken into account by calculating non-affine. So these are the displacements minus the affine displacement. So you remove the affine displacement. What you do is you look at the linear response. You shear. Here what they did is they shear a tiny bit the system. They reminimize the energy, look at the displacement, subtract the affine displacement, and look at the difference. And you see that you have non-affinity, and this non-affinity is associated with a change of the modulus, of the moduli. So I'd like to show you that. Yeah, so that's another example. So you have your favorite system in a certain initial strain. And so that's a fine shear. So this is a deformation tensor, and so essentially each particle is changed by the deformation tensor. When you minimize the energy, now you have something a tiny bit different. Yeah?
To avoid the global
crystallization. Yeah. Yeah.
Adiabatic simulations or?
It is AQS.
So, okay,
Just what I described. No. Okay. Again, I start from a configuration. Here I shear affinely. I just bring the particles to the position specified by the microscopic strain. That's it. Oh, there are periodic boundary conditions, yes. Now, I minimize the energy. So I'm just decomposing the step I was showing you before. You know, I strain affinely and then I minimize. So here I strain affinely, now I minimize. Now I subtract the, I just strain backward, and there is a residue. And this is a displacement field. If I take a larger system, I have this very large non-affine displacement. So I'd like just to take the time to explain you a bit where this comes from. And because what I would like to show you is to show you that it exists in the linear response, right? Because often the question that comes up is people say, oh, but that's how much you strain, and no, it's a property of the linear response. And I would like to take the time to show you why. So the idea is that we have this potential energy, which is a function of position, and I will consider, for simplicity, I have a single strain parameter. It's pure strain, it's shear strain, it's whichever you like, it's your strain parameter. Then I will assume that I will add a prime here to say that I will decompose the motion into affine and non-affine. So the idea here is that the prime only captures the non-affine part. And so it means that if I change gamma without changing this, the system is shearing homogeneously, affinely. Right? And this is, we can work the detail, but it doesn't matter. It's just that you can parameterize your energy function by non-affine, by displacements, which are non-affine, and by the strain, which captures all the affine response. Now, the forces, of course, so maybe first, the force is on particle I, it's minus du dri. Okay, and I remove the prime because it's inconvenient. So, but okay, the point is the positions are just the non-affine positions, right? To only capture the non-affine part. So the forces are just minus the derivative of the potential. And of course, this is zero because I only look at mechanical equilibrium states. Now, the stress is, of course, the derivative of the, so, yeah, and so I will introduce a total derivative, which means that I derive the potential along the path of the local minimum. So when I'm saying this, I'm saying that these positions depend, these non-affine parts of the position depend on strain when you follow the local minima. So if I shear, my position will slightly, my non-affine part of the position will slightly vary in order to guarantee minimization. So stress is the derivative of the potential. The total derivative I write here means that I follow mechanical balance. So now you just write that this is du d gamma plus du dri by d gamma. I just do simple derivation. And this is the force, which is zero, so this drops. So the stress is just this. It means the stress is just the stress you would get from the affine motion. Now, the modulus is the second derivative of, yes?
I'm lost. So when you write the force is minus du over dr, where r is just the affine part.
Yes.
This
Okay.
is if u is not
maybe.
the whole u or whatever, no?
Could I write that ui gamma, the non-affine displacements?
Yes.
I'm just saying that the positions is at a certain gamma is a non-affine part, an affine part, which is a tensor of gamma times Ri of 0 plus a non-affine. Okay. And so instead of writing my energy in function of gamma and R, I write it instead of gamma and U.
That's fine. But then when I have to calculate the force on a given particle, in principle, I should take the derivative of the potential with respect to the actual position, not just the affine part, the non-affine part.
The force you calculate at fixed strain.
At strain 0.
No, at any fixed strain. It's just you don't change the strain. You look at the force for a given strain.
Okay.
So you look at, so you say, let me say fixed gamma fixed, and I take a derivative. You can say, okay, I take the derivative, okay, let's do this. I take a derivative with respect to Ri at fixed gamma. So if gamma is fixed, this is fixed. And d by dri is just the same as du. No, that's a very good question. It's a delicate point. Du by dui. It's very important. Okay? So now the modulus, okay. Yeah, so I erased that? I erased that. So now, let me just first look maybe at the non-affine part. I want to say that the forces are always 0. So now, what I will do is I take the derivative of this once more. So I take d by d gamma of Fi. With a minus sign, it's more convenient. So I just take the total derivative of this. This will be d square u by dui d gamma plus d square u by dur duj by d gamma. Again, I use series of derivative. Okay? Now, this is the Hessian matrix. Sorry, this is the Hessian matrix. It's a matrix of second derivative. This is something which is, I call that psi I. This is the variation of the force during a fine strain. It means that if I take the system, so the point is that when you take your system and if you shear finely in the linear response, there is a force residue. Right? So this is, again, that's the change of the force caused by the affine response. So the point is that when you shear finely, you do not guarantee that the forces remain zero. That's the whole point. Because of elastic heterogeneities, because of structural heterogeneities, and so on and so forth. And so now you have, and this is your non-affine field at the variation of ui by gamma in the linear response. So you invert that, now you find that dui by d gamma is just, so that's duj, sorry, so it's du by d gamma, minus is the inverse Hessian on this, so duj, say it's hji psi I. So the non-affine part is the non-affine field comes out in the linear response as the inverse Hessian, so it's like an elastic response. When you invert the Hessian, you look at the elastic response of your system to these forces, to these imbalances caused by affine shearing, right? So now, what I want to arrive at, because I think that's really crucial, is that if you take a modulus, I'll call it mu for simplicity, and the modulus is a second derivative of the potential. So now I derive stress. And I play the same game. So now I derive stress, so I take the total derivative of that. So it's d square u by d gamma squared plus d square u by d gamma dri by d gamma. So here we find, again, this psi field. Here we have the second derivative of the potential of phi. This is the Born modulus. This is the modulus you would get if you assume a fine response. And now you have a correction, and now you have dr by d gamma. I plug that in, and this comes with a minus sign, psi h minus 1 psi. And so you have a negative correction to the Born modulus, which comes from non-affinity. And the whole point is that non-affinity softens, it changes the modulus, it causes softening, because in fact, simply the point is that if you shear homogeneously, finely, you're not in a minimum. And so you minimize a bit your energy drops, and the curvature is a bit weaker, and it means that your system is a bit softer than predicted by the affine response. Is it clear for everybody? No? So I wanted to go through that yeah. The elastic response is reversible, as I said, totally reversible. So you can shear back, so long as you are along an elastic branch, it's completely reversible. So here that was a very, I just simplified a lot the calculation by looking at a single strain, by passing some details about how you change variables. The point is that this formalism exists. The linear response of solids can be entirely calculated. It's just second derivative, right? It's nothing else. It can be entirely calculated, and it means that in practice, when you do numerical simulations, if you have an inherent state, if you have any configuration, you can calculate any modulus just analytically, okay?
I know that I can think of non-affinity arising from fluctuations, spatial fluctuations of elastic modulus, the soft parts, the stiffer parts, and so forth. Where do I read spatial fluctuations of elastic modulus in there?
Here. That when you shear homogeneously, you cause force imbalances because of these heterogeneities. If you have as you were drawing some heterogeneous spring, if you assume a fine response, so you have two springs and you stretch them the same amount, and then one of the forces of the stiffer string will be larger than the one, and so on the point that between them you create an extra force. And that's the cause of the non-affinity. The source of non-affinity. And then the non-affinity, its forces proper, you can see as the elastic response of this spring system to this force imbalance. Of the stress, yes. You can see this as this is really the
derivative of du over d gamma, which
yeah, I prefer to see it as the d by d gamma of the force. D rho by d gamma, which means the change of the force under a fine motion. Otherwise, it's a bit complete. Yeah, it's really easier to understand like that. You have the, I could revert that. So it's d by d gamma of the force, and so it's how the force changes during a fine motion. And in a crystal, for example, in cubic crystal, you can show the symmetry that if you look at the elastic, at the homogeneous response, you don't create forces because of symmetry, and then you don't have non-affinity, right? There are lots of things that can be drawn from that. For example, when you have power law potentials, you have some simplifications. You can show, for example, that if you have a pure power law potential, there is no correction to the bulk modulus. So if you do compression, if you have a pure power law potential, if you compress, you don't change the forces. And so you don't have non-affinity associated with compression in a power law potential. Right? So there are a number of results that come out from this formalism. Okay? Yeah. Sorry? Because the force is always zero. By definition, we track local minima. So it's just like implicit function. It's the, you know, that you have an implicit function and you try to okay. Good, so okay, that's just a summary. Yeah, maybe that's just to show it. This is this psi field. So here you have a system. I just look at the response to, I don't know, shear. This is the psi field. And so you see it's very, very disordered. I've been thinking for years about how I can use this to try to construct some approximation to modulus, never succeeded. So it looks very disordered, but it's not so disordered because it really is associated with the Hessian in some very strange way. And then this is the Hessian response to this. And it's much more soft because essentially you pick up when you inverse the Hessian, you pick up the lower frequency, you have dominant contribution of lower frequency modes. And then this is why you have something that looks very smooth, and this is your non-affine field. So I think the two key statements are first that non-affinity is a property of the linear response. And the second key statement is that it softens the system and that it has a direct effect of elastic moduli. Maybe a third statement is that's more technical, is that we can calculate all of that, and it's of course very convenient in simulation. And so that's just to summarize what I was saying. Okay, so now what I'll do is, so we have looked at the elastic response, and we progressively are going to towards the plasticity. So again, plasticity occurs because I just hear the same sketch as before. The system is in a local minimum, and then you reach a local instability, and this instability is a saddle node bifurcation. So because you have a local direction, which becomes, so you have, in fact, here it's a saddle node in the sense that you have this local minimum, and at some point between these 2 points, the system is flat, and it means that you have locally one eigenvalue, which is 0. So because you have this eigenvalue, which is 0, so I just said before, this non-affine response is it's written here. It's the inverse Hessian on psi. Is a missing minus sign? Yes, okay. So the non-affine response is minus h minus 1 psi. And because if you have a mode that vanishes, so when you inverse the Hessian on something, you have a sum of the inverse of eigenvalues on some coupling coefficients. And so it means that you have the non-affine field becomes very focused on the unstable mode. So what happens is that the non-affinity will concentrate on the non-affine mode. And this is typically one of the non-affine mode, and I'll come back to what is a physical interpretation of that later. But that's typical, and so what you see that this mode is highly localized. So you have this onset of plastic events, which is associated with the concentration with the vanishing of an eigenvalue, and the non-affine field concentrates on these eigenvalues. And that will be important for later. It turns out that now so here you have an elastic branch and a jump, and here we're looking at the tip, the very end of the elastic branch. And look, here that's a strain with reasonable units. This is strain with totally unreasonable units because I'm looking on very, very narrow focus that experimentalists would never dream of achieving. But the point is that when you look at this, you see that there is, in fact, you can, from this argument, you can deduce that you have a scaling of the stress, and you have a scaling of the energy when you approach threshold, and that will be important for later. And so you see here that there is a square root singularity of stress, and we can really see it, and we see it at every end of elastic branch. There is a nice square root of singularity. Okay, so instabilities at work. This is a video. This is the non-affine field as we approached instability. So it's a short movie. So that's a system where, and what you see. Let me start again. So what you see that you have, when you approach an instability, boom, you have this non-affine field that localizes on the unstable mode, and maybe something here, and then another instability. And after the instability, the system is much more stiff. And you see that after instability, you have stiffened your system. But you see these dynamics of the system going through instabilities and localizing every time. Yeah. Okay, so that's a very good question. I could have pointed that out. using this, you can try to predict. We did some, you can, in fact, it's quite amazing, but you need to, not the pattern alone. Okay, first of all, what I'm showing here, this is an unaffine field, and the other squares are contribute, because the non-affinity is the inverse Hessian. And so you can decompose that into contribution of different modes. So that's the full non-affine field. And these are the contribution of different modes and higher order modes. And so if you look carefully, you can see that, for example, this guy is already, there is some instability that are already can be seen in higher order modes in some cases. If you want to predict the occurrence of instabilities, you need to go, you need to use a higher order derivative of the potential energy surface. You need to go up to third order at least. When you do that, if you know how, if you can calculate your potential energy at higher order and use this relation, you can really essentially back out this relation to try to guess the instability. A bit strikingly, at the beginning of every elastic branch, you can guess where it ends, just by looking at the high order derivatives of the potential energy surface. Of course, this is, yeah, I don't know what to say. I mean, we can do it, so then that's it. Yes. Yeah. When we predict, we can predict where it occurs. We can predict but again, it requires higher order derivatives. There is, Anael Lemaitre has worked a lot also on that. I mean, really expanded that over the years, where we're trying to look at spatially resolved higher order derivatives in order to get information about the instabilities. The answer is yes, you can. But then you need to have higher order derivatives of potential, which means a system with many parameters. And so the problem is how you can, okay, it's technical, but you can. Yeah.
I did not explain.
Let me say why it's soft. It's soft because you approach an instability, which is a saddle node, and at the instability, you have a zero eigenvalue. So it has to be soft when you approach the instability. And after you pass the instability, it's no longer there. So I think it's reverse, right? It's that because you have a series of instabilities, you have to go to a series of soft modes. Each instability is a localized soft mode. So each instability is associated with the vanishing of the modulus in a small region. After you pass this instability, this region in general becomes meaningless. It's just like others. Okay, so okay, finally, let's look at plastic events. So, that's the energy here. So energy, so these are branches of parabola, but you barely see the curvature. The system is large enough. And so these plastic events correspond to drops of stress and drops of energy. So how do we do this? Again, we bring a system continuously through the potential energy landscape. At some point, the system becomes unstable, and what we do here, we just minimize the energy. When the first talk I gave a long time ago on that, people were asking lots of questions about how you minimize, and how, of course, it might depend on how you minimize. The detail of an event depends not only on how you minimize. We did something, we were saving at the time, more than 20 years ago, right? So we were saving data in ASCII. And so we save and we restart, and we realize that when we restart, we did not get the same event than if we did not stop if we run the simulation. Because the error, the problem is that, so you have a system which is on this potential energy surface. And so at some point it becomes unstable, and then it slides in the surface. And it's a surface which is in this n-d-dimensional subspace with all sorts of positive, negative curvature. When you are no longer at a minimum, you have negative curvature everywhere. When you have negative curvature, you know you have amplification of trajectories, nearby trajectory diverge. This is chaos. So you have Lyapunov exponents. That would be something interesting to do. I always dreamed of looking at the Lyapunov exponents during the descent. The result is that the detail of where you get to depends on tiny, tiny things, because it's a chaotic problem when you jump from a minimum to another one. The statistics of the result don't. I mean, and we have done that with lots of methods, and people have done that using different methods. It doesn't. What you see systematically, and here you have a large system, and the point here corresponds to places where you see a significant rearrangement. So we measure that by, I don't remember what, by some fluctuation of the local, I mean, maybe the d-square mean criterion for those who know. So what you see is that if you look at, first of all, if you look at energy versus, so that's the number of minimization steps. And so you see that the minimization of energy is very intermittent. And if you look at F, the square force is just is the equivalent of the rate of, yes.
It zoom in on this red.
Exactly.
Or
So I just take this guy. Thank you for your question. I just take this drop, and I look what happens during the minimization. So every step I minimize energy, right? I take this drop and I look at what happens to energy during minimization with conjugate gradients. What you see is that you have something very intermittent. Here the system is escaping very slowly the unstable point, and then finds, boom, something interesting, and then da-da-da-da-da, and then at some point believes that maybe, can I stop there? Should I stop? No, it's still not flat enough. And so on and so forth. You have this burst of energy dissipation, which show that you have this intermittent dynamics of energy of descent. So again, now if you look in real space, you see that you start from here, the center, look, that's where it starts. I just run it again. And then it expands. And it expands along something roughly linear, not exactly, with a lot of disorder. And so what you see that during the plastic event,
The process, the direction of shear here is.
oh, sorry, the shear, that, so, or maybe like that, I don't know.
Like this.
Yeah, exactly, yeah. So, so you have an avalanche, something that looks like an avalanche. And if I want to say it's an avalanche, I need to show that statistically. It's harder work. It has been done over the years. So before I do that, I would like to point out one thing, that in fact, if I want to characterize avalanche behavior, I need to look at system size effect, because when you have avalanches, you have the trace of avalanches that you have some strange scalings of fluctuations of system size effect. So the first thing I do is, so sorry, the picture is a bit ugly, it's old, but here you have stress versus strain for different system sizes. What you see that the blue is the larger system size, the black is the smaller one. And so what you see is that, of course, that's expected. As the system size grows, the fluctuation decreases. And so you reach your plastic, your elastoplastic curve. So you have this sawtooth pattern, and as the system size grows, these sawtooth patterns becomes finer and finer and finer, and that's how you reach plastic flow. But plastic flow, macroscopic plastic flow, is the endpoint of a sawtooth curve with elastic branches and plastic events. Now, over a strain delta gamma, on average, you increase the stress by the modulus times delta gamma. So the rate per strain, the increase of stress by unit of strain is mu. That's what the modulus is. Now, here we release the stress by drops. And suppose that I denote delta sigma, the average stress drop, and delta gamma, the average interval between drops. So the rate of stress drop, of stress release, is essentially delta sigma by delta gamma, and this has to be, if I have in steady state, I'm only looking at steady state, the rate of increase, the elastic increase of stress has to be equal to the plastic release of stress, and it tells me that the stress drops and the intervals between drops have to be related. Now, if you had local events, imagine that plasticity results from very local rearrangement, totally independent of each other. Then what you expect is that if you increase the volume of the system, the number of events in a unique gamma strain gamma goes like the volume. And each event releases stress in a small neighborhood of size, fixed size. And so the stress is this normalized by the volume, should go like 1 over the volume. So if you had local events, the stress release and the interval should decay like 1 over V. That's not what we see, and that's really the trace of avalanche behavior. And the fact is that, so okay, I just cite one reference there, I'll cite many others later. In fact, no, there are some exponents, and there is a whole literature now on what exponents are, and well, there is, there were lots of efforts in that direction. Now the point is that, in fact, the fluctuation, so the system converges towards a continuous curve, but it converges not as fast as if events were independent. You have much larger fluctuation than you would have if events were independent, right? And so that's also a trace of this. So that's a direct trace of this avalanche behavior. So here I just refer, I think this is from Salerno and Robbins, if I'm not wrong, so in 3D, so some scaling with system size, and there is a whole lot of literature. I like this picture, it's from Salerno, I think it's, or maybe Malone Robbins. That's the rotation, that's the local rotation in a very large system, so you can see very developed avalanches. Yes?
So do you have things like you have in earthquakes, for instance, where if there is an earthquake in a given place, then there is an increased probability to have another one in the same place, but only for a given time? Like these hot spots.
That's an excellent question. Actually, I saw
a talk by Ludovic Berthier recently, and he just is looking at this. So, and yes, there is. That's always a question we had in mind. We never looked at it in detail. There is for a while, and then it stops. And maybe later we will see cases where this matters.
Why would you expect, if you go to the next slide, why would you expect a steady state and not something like you have mu that changes with a very large strain?
This should have been clear. I focus on steady state.
A steady state, and why do you expect to have
when you do an experiment, you cannot avoid, when it happens, failure. And in that case, in a simulation, even if we produce very brittle systems, now we can, eventually, if you have periodic boundary condition and you shear the system, eventually you always will reach a steady state. Maybe it will require a humongous amount of strains, but the volume is fixed. The system is forced to shear, and it cannot really break. And if it cannot really break, you can always reach eventually a steady state. I will point this out. I haven't talked about transients, and I have a few slides on that. Yeah.
Yes, avalanches and so forth. So I'm just a little bit confused. You focus on the part in the oval,
Yeah.
and that's on the bottom left graphs, these 5,000 steps. But each step corresponds to a full minimization.
No. This is the step along the minimization procedure.
I just look at a successive set of states and I minimize the elastic energy, the total energy, from one state to the other one. So my life is much simpler, but I can't tell anything about what happens between steps. I thought that this was the moral contract.
I can what? I can tell or I cannot?
I cannot.
Well, what happens between steps?
Right.
Oh, you mean you cannot tell that? What happens?
I cannot. I mean, I can of course plot the bottom left plots,
Yeah.
but it's not clear to me what is the physical meaning of that.
We will come to this really shortly. All the problem, all the dissipation, again, the dissipation occurs only in plastic events. So all the complexity is concentrated in plastic events.
Right.
Now, I mentioned that if you change the initial conditions, you have something slightly different. But let me say one thing. Imagine you do, instead of minimization, we could do damped dynamics. So we could introduce physical dynamics. The system, I would like just to point one thing out, is deterministic. Right? So this series of events, it's complex, it's chaotic, but it's deterministic. But you're right. What happens during a plastic event is really complicated. And this is where all the physics of plasticity. Yeah.
Why would you say that the system is deterministic? When you have zero in the spectrum of H, then the size of thermal fluctuation.
There is no temperature, there is no thermal fluctuations. Yeah. I will come
This
later.
idealization breaks down exactly at the process that you're interested in.
So you are asking a question: what is the role? How this is robust to thermal effects? Yeah. Yeah. So you're saying that this whole picture is not robust to thermal fluctuation.
Plastic should be robust, but the plastic events should be sensitive to thermal.
Okay, I'll come to this later in next lecture. We will see that it is very robust and up to an enormous temperature. Okay, so the details of each event is sensitive, of course, would be sensitive to thermal fluctuation, but the driving mechanism behind that, maybe let me say one thing, the fact that the reason you have an avalanche. Oh, okay, yeah, I'm reaching the point of, yeah, that's where I'm reaching. So what happens? Okay, sorry for that. So we are arriving at some interpretation. We have data, and so what happens? And in order to interpret this, we need to get back to what people were expecting about the mechanism of plastic flow. What people were expecting from a long time ago about plastic flow is that it results from, well, there is a whole history and many erroneous ideas. So let me just cite one, which is stays. And so, which is this idea by Ali Argon. And in fact, it also related to a discussion on glasses and some ideas by Goldstein that I'll mention later. So this idea by Ali Argon that essentially the plasticity is expected to result from local shear transformations, from local rearrangements in the material. And this was also supported by, for example, observations on foams, where you can see that you have these T1 events where you rearrange cells. And so that the idea is that the plasticity, the phenomenological picture we have of plasticity, is that it should result from local rearrangement. So when you look at avalanches, in a certain way, you might think that, well, it doesn't look at all like that. It looks like something much more complicated. But so there is behind this idea of rearrangement, and Argon was noting this, actually not in the initial paper, but a bit later. There is the idea that, so there is a concept that we need to discuss, which is I think it was mentioned, but I'd like to come back on that. It's the notion of Eshelby transformation. So this idea comes, so in the context of study of polycrystalline systems. Eshelby is studying martensitic transition. So martensites are some kind of crystalline states, and which under temperature can change their crystalline conformation. So you have a crystal that might change its, so you have, imagine you have a local crystalline inclusion in a polycrystalline system, and this inclusion, when you change temperature, changes its crystalline structure. So you have a material where you have an inclusion, which is, and the system you imagine initially is stress-free. And this inclusion, and this is drawn here, spontaneously changes shape. And of course, it's related to what we're going to discuss, because when you have a rearrangement, this is just what happens. You have local packing, which changes shape. What happens around that? What's the consequence for the material? And so Eshelby has this outstanding argument. So he says, okay, so we want to understand what is the result of the transformation of this inclusion on the whole system. So Eshelby says, okay, we start from a stress-free state, and imagine that I cut out the inclusion. So if it's stress-free, I can cut it out, I remove it, I have a hole and an inclusion. Okay. So I have a hole and I have an inclusion. Now my inclusion is changing state. It doesn't fit in the hole. So what can I do? Well, I can take imagine you want to fit something in a hole. That happens, right? Sometimes you're doing some work, and so you take the inclusion, and you just apply stresses to bring it to its initial shape. And now you fit it, and you hold it. So you take the inclusion, you stress it to bring it back to the initial state, you put it back into the system, and so long as you hold, the system around doesn't know there is an inclusion. Right? So there is nothing, the system around, but you are holding. So you have to stop holding. And so the fantastic idea is to realize that if you let go, it amounts to, so here you have an elastic system, homogeneous, continuous, so you assume, of course, you don't have elastic contrast, so you have an elastic material, homogeneous elastic system. with a set of forces. And strain is 0. Letting go amounts to adding the opposite forces that you are applying. That's all. So letting go means you add the opposite forces. So you start from an elastic system, homogeneous, 0 stress, 0 strain, and you apply just the opposite forces than the one you need to twist strain the inclusion back in its original shape. And then it turns out, so essentially the result of the transformation of this inclusion amounts to introducing a set of forces, of localized forces that act on the surrounding material. Yeah. Yeah. So the problem is that he studies the problem of a spontaneous transformation of an inclusion. So that I was referring to Martensite. In Martensite, you can have a change, a thermally induced change. You change temperature, and the system changes from, I don't know, phase-centered cubic to centered cubic or something. So you change the shape of, and because of that, you change the shape of your crystal. So you have a system which spontaneously undergoes a transition that causes it to change its shape. And this is what we have when we have a rearrangement in a glassy system. So that's the starting point. And now the question is, when this happens, what is the consequence on the rest of the system? And so the argument is, so when this happens, so you exert these forces to fit it back in, and now you just let go. And so it turns out that the result amounts to adding some set of forces. And so it's the elastic response of the system to forces on the edge of this inclusion. Okay? So you can calculate this. This is some paper by Picard and others. But okay, so I'm sorry, this is not the best picture I have. I could have found something. So essentially, the shear stress, the point is that the shear stress associated with this has this quadruple form, so it's cos 4 theta. So essentially what it means is that if I have a shear here, I will increase the shear stress along the horizontal and the vertical line, and reduce the shear stress along the diagonals. And so that's why you have this cos 4 theta. People often speak about quadruple. It's not a quadruple. Right? It has a quadruple shape, but it's the response to a set of forces, and this set of forces is a dipole. So that's something very strange, is that when you introduce, in terms of, if you construct an analogy with electromagnetic, this set of forces corresponds to an elastic dipole, and the elastic response of an elastic dipole turns out to have this cos 4 theta symmetry, right? So I'll be speaking of, you often will hear people speaking of the Eshelby quadruples. I will speak about Eshelby dipoles, which have yes? A quadruple means you have a gradient of dipoles. When you have a quadruple, it means that if you do electrostatics, you have a charge, two opposite charges, that's a dipole. If you have other dipole at the same location, it's still a dipole. If you want to have a quadruple, you need to have a pair of charges and another pair of charges, and look at all this, and then you have a quadruple. This is not what we are looking at. It's still a dipole. I will maybe, I will come back to this later, because next time, in next talk, because I can construct a more, in fact, now there is a much more formal way to understand that. But right now, I just want to talk about plasticity. And so I just introduced Eshelby, and I will show you later that all these can be really grounded on something much more rigorous. Okay, but let's say these are the ideas that are hanging around, and that's enough for now to have an interpretation of these avalanches. So the idea is, so you take a system, for example, I showed you this eigenmode, this mode leading to instabilities, and this mode leading to instabilities, it's really the expected displacement field. You can take a cut through these lobes and you find the expected radial dependence. This is another, from another paper, something where people looked at the stress change, and you can find here this signature of quadruple. You have these lobes here, and well, it's a bit hard to end in the diagonal. So we see Eshelby events in the plastic response. The point is that when we see that we have avalanches, it means that avalanches, of course, are not single Eshelby events. They are cascades of Eshelby events. And this, in fact, is of shear transformations. And this is really consistent with the idea precisely that, so when you have a shear, so you shear your system. At some point, there is a region which yields. Now, when this region yields, what happens is that it increases the stress along the horizontal and along the vertical, and reduces stress in the other direction. So now imagine that farther away, you have another region which itself is very borderline, is very close to instability. Now, this first event occurring can push the other region beyond its instability and trigger a secondary event. So the observation of avalanches, in fact, was the direct proof that Eshelby mechanism is at work. It's the fact that we see avalanches demonstrates that events talk to each other, that different regions of the system talk to each other, they interact, and the only way they can interact is through stress, right? Because that's what you propagate. So you have this change of mechanical balance. So now it also means that for that to be at work, you need to have a reasonable number of these regions which are very close to threshold. Because if you have just, if it's extremely rare, then your stress field will not trigger secondary event. It can trigger secondary events because you have other zones which are arbitrarily close to the threshold. And why is that? Well, simply because you shear. If you're in steady state shearing, what happens is that you're constantly driving the system towards these instabilities. You have one instability that trigger a plastic event, but all the regions of your system are progressively driven towards instability. So you bring your system in a marginal state where you are feeding in a population of near threshold zones. And then what happens is that when you have one event and it triggers this, and then you have this elastic field, that Eshelby field that propagate, and then it will trigger secondary events, and that's how you find an avalanche. Okay? And so the picture coming from, and so you have lots of works. This is by Lennard. I could find many other, or people who are started to look at the distribution of how close to threshold you are. What is the distribution of, what is the distance to the next threshold? So you take all sorts of configuration from steady state, and you measure the distribution of the elastic branches, of how far you are to the next threshold. And you see that you have a large tail. When you are in the steady state flow, you create a large tail of zones which are near threshold, and this is really key to the fact that you have avalanche behavior. Yes?
Maybe it's a stupid question. But you said for avalanches, I understand you have to have long range elastic fields. Why should it be on the same type, the same parabol? Why should it be of Eshelby type and not any other stress field, long-range stress field?
I'll answer that next time. Oh, you're not there? Oh, that's bad. No, next to the, sorry. So, okay, so a short answer. The short answer is it's possible. In fact, it's if you look at just one inherent state and you look at the stress field, even not strain, just you take a glass, you quench, and you look at the stress field. So it's isotropic. You have the stress field in a glass is long-range correlated with the 1 over r squared in 2D correlations. And you can prove that this is required by mechanical material isotropy and mechanical balance. And the fact that stress fluctuations are normal in the sense that the stress of a volume, the fluctuation of stress of a volume decay like the inverse volume. If you have these three conditions, you can prove that the stress has to be as 1 over r to the d correlated in any disordered solid. And without resorting to HLB. So, oops. Okay, so I'll just finish. I'll conclude with a few things. There are mean field models that try to benefit from that. So by looking at the population of zones and trying to understand the near threshold dynamics. So essentially you have models where you say, I have zones, and so threshold is here in that graph, it's here in the other graph. So I have zones, and when the zone flips, it creates noise. I mean, noise is these HLB stresses, create some kind of elastic noise on the other zones. And so you can look at the dynamics of this population and try and understand, for example, the avalanche dynamics. You have elastoplastic models where people try to now look at the elastoplastic response. So you have systems where you imagine you have like spin-like systems with many sites, and these sites can, where you can trigger events, you can construct a variety of rules how you trigger the events, and then introduce these HLB fields, and you do produce avalanches. And then maybe, yes, that might be a good time to stop. So what I have, yeah, no, maybe, oh yeah, I will just show that. I want to show that because just to show that the connection with experiments matters. So first, I love this. This was a paper on foams, and you see that you have people were accessing actually the quasi-static regime in sheared foams. This is a paper by Peter Schall and others where they also were looking at these HLB events and trying to look at the local strain, and they have indication of the HLB field. So, and that's a more recent paper where people look at the strain granular medium and they find indication of also of correlation, HLB type correlations before the occurrence of the formation of shear bands.
Very quick question about the foams. Is it correct to say that in a foam, the HLB events are E1 transitions?
Yeah, well, okay. You have T1 transitions. You may have 2 T1 transitions occurring simultaneously. How do you call that? And it will lead to an HLB field. And the thing is that any event will lead to an HLB field. This is really general, whether it's T1 or anything else. What is always true is that you have HLB. Maybe it's a good time to stop. I think it's, is it? Yes? Yeah.